Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from Deshbandhu College, University of Delhi. Today we are going to discuss about the module that is generation and recombination processes in a solar cell. From the paper Energy related materials. So students, the main point which will be covered in this module are: number 1, what are p-type and n-type silicon? Second, generation of electron-hole pairs after the absorption of light. Third, what is electron-hole pair recombination? Fourth, types of recombination process. So let us start with a brief introduction about this module. A semiconductor is a material whose conductivity is intermediate between a conductor and an insulator. At room temperature, the resistivity of a semiconductor varies between 10 to the power minus 3 to 10 to the power 6 ohms per centimeter. However, that of a good conductor and a good insulator, it is of the order of 10 to the power minus 6 ohm centimeter and 10 to the power 12 ohm centimeter respectively. A conductor has a positive temperature coefficient of resistance, whereas a pure semiconductor has a negative temperature coefficient of resistance. The Ohm's law, which is relating the current flow through a conductor and the voltage across it, is not valid in the case of a semiconductor. So adding a very small amount of certain impurity atoms into the pure semiconductor materials can generate sufficient free electrons and holes. These impurities can alter the electrical property of the material significantly. The process of adding these impurities inside a semiconductor is known as a doping. A pure semiconductor material, when subjected to the doping process, is termed as an extrinsic semiconductor. So depending upon the type of the doped impurities, extrinsic semiconductors can be divided into n-type or p-type semiconductors. Next important phenomena is the carrier generation in the case of semiconductors. Carrier generation is a process where electron-hole pairs are created by exciting an electron from the valence band of the semiconductor to the conduction band, thereby creating a hole in the valence band. Whereas recombination is the reverse process where electrons and holes from the conduction band recombine and are annihilated. So in the case of semiconductors, several different processes exist which lead to the generation or the recombination. The most important ones are photon transition or optical generation or recombination. Band model of silicon. The silicon semiconductor belongs to the fourth group of periodic table that has 14 electrons, out of which the outer four can be given to, accepted, or shared with another atom. These four electrons are called as the valence electrons. Hence, in order to form a solid, many silicon atoms can bond together through their valence electrons. In so formed solid, each silicon atom shares all of its four valence electrons with the neighbor silicon atom through covalent bonds. Each silicon unit, which is formed by a tetrahedral arrangement of atoms, contains five atoms, that is, one silicon atom plus four other neighboring silicon atoms with which it shares the electrons. In a silicon solid, each atom is held as the fixed position from another atom with which it shares a covalent bond. Such structure, which is formed by periodic and fixed arrangement of atoms, is called as a crystal lattice. The figure on the right hand side shows the unit cell of a silicon crystal where the atoms are located so as to form the vertices of a cube, with single atom centered at the each of the faces of the cubic pattern. The cubic pattern or the arrangement repeats throughout the crystal to form a bulk. Now the below figure shows the schematic of the silicon crystal lattice where two silicon atoms are bonded with two shared electrons. Doping in semiconductors leading to the formation of N-type and P-type semiconductors. As we have discussed earlier that the semiconductor materials, they have poor electrical conductivity that needs to be enhanced. Hence, in order to improve the electrical conductivity, some foreign atoms are introduced into the intrinsic or pure semiconductor crystal. This process of introduction of foreign atoms into the intrinsic semiconductor crystal is called as the doping. Now suppose by some means if we dope the pure silicon crystal by substituting a silicon atom with an atom from group 5, for example phosphorus, which is having 5 valence electrons, then the phosphorus atom would occupy the same position as that of the silicon atom in the crystal. This is clear from the figure on the right hand side, where the yellow colored sphere is showing the phosphorus atom, which has already replaced the silicon atom. The 4 valence electrons of the phosphorus atom will be shared with four neighboring silicon atoms through the covalent bonds, whereas the fifth electron will remains unshared as it could not find any open bond in the crystal. This extra electron is relatively free in comparison to the bound electron, which is weakly connected to the nucleus, and at room temperature there is enough thermal energy in the crystal to shake this electron loose. This free electron is always ready to be a part of an electric current in the semiconductor. Also, this extra electron tied to the phosphorus atom lies at an energy EI just below the edge of the conduction band, which is shown in the figure. That is, this extra level has been created due to donor energy level or the donor impurities. So, a silicon crystal which is doped with many phosphorus atoms will have many free electrons. Hence, the electrical properties of the crystal will be altered drastically. Impurities introduced in this way, they are called as dopants, and the built-in foreign atom is called as a donor atom because it has donated an electron to the crystal. Such semiconductor materials which are doped with pentavalent or group 5 impurities or donor doped are known as N-type semiconductor materials. This donor atom more or less presents the crystal lattice with one free electron. The donor atom has four bounded electrons, and at the same time it has five protons in the nucleus. In total, it is a site-fixed positive charge. Increase in the doping facilities, more number of free electrons, and almost no holes left in the semiconductor crystals. Hence, electrons in N-type semiconductors are called as majority carriers and holes as minority carriers. Practically, the concentration of the free electrons in N-type semiconductors can be determined by the density of the donor atoms, that is Nd. Now, students, there is another possibility of altering the electrical properties of pure silicon semiconductor is by doping it with the atoms from group third of the periodic table, example boron. In this case, one bond remains incomplete as boron has only three valence electrons. Therefore, there is a missing electron on a neighboring place, giving rise to a hole tied to the boron atom. So this is evident from the figure also, where there is a gray hemisphere shows the boron atom. As discussed earlier, holes can move freely like electrons in the conduction band. Hence, the silicon crystal doped with many boron atoms will result in many holes, which will act as free positive charges moving throughout the crystal. This trivalent impurity in silicon crystal is called as acceptor, as the holes they accept electrons from the rest of the silicon crystal. This acceptor-doped silicon semiconductor material is called as a p-type semiconductor. Any free electron in the p-type semiconductor material is referred as the minority carrier and the holes as the majority carrier. Now, as you can see from the figure also, that in a p-type semiconductor, the impurity atom give rise to an allowed energy level in the forbidden gap just above the edge of the valence band. Carrier densities of acceptors and donors. The total number of electrons and holes in the conduction band and the valence band, respectively, can be found by considering the following equations for charge neutrality in a semiconductor. That is, the equation is P minus N plus Nd plus equal to 0 and P minus N minus Na minus equal to 0, where Nd plus is the concentration of ionized donor atoms and Na minus is the concentration of ionized acceptor atoms. The addition of donor or acceptor impurities does not change the overall macroscopic charge neutrality of a semiconductor crystal, and hence it satisfies the following condition, that is P plus Nd plus minus N plus Na minus is equal to 0. The other important equation is as follows, that is N multiplied by P is equal to Ni square. For semiconductors with dopant levels close to the band edges, nearly all the donors or the acceptors are ionized at room temperature. From the first equation, that is P minus N plus Nd plus, it is clear that since the vast majority of donors will be ionized, that is Nd plus will be nearly equal to the total density of donors Nd. Furthermore, N will be greater than P when Nd becomes larger. Hence, it can be written as that Nd plus is approximately equal to Nd and the small n is approximately equal to Nd. So, P will be approximately equal to Ni square by Nd, very much less than N. Similarly, for the acceptor ions, we have Na minus to be approximately equal to Na. Hence, P will be approximately equal to Na. So, N will be approximately equal to Ni square by Na, that is very much less than P. So students, till now we have discussed about the doped semiconductors. Now let us discuss about the location of Fermi level in a doped semiconductor can be established using the initial equations. So, for N-type semiconductor, our N is equal to Nd, that is equal to Nc exponential Ef minus Ec by Kt. So, Ef minus Ec will be equal to Kt ln Nd by Nc. And For p-type semiconductors, P is equal to Na and it is equal to Nv exponential Ev minus Ef by kT. So, Ev minus Ef will be equal to kT ln Na by Nv. So, it is clear from the Fermi level energy as a function of donors and acceptor concentrations, that is, the Fermi level energy for donors shift upwards from the mid gap and the Fermi level energy for acceptors shift downwards as compared to the mid gap. Now let us discuss about the electrical conductivity of semiconductors. The conduction in a semiconductor material occurred due to the flow of both electrons and holes. Hence, the electrical conductivity, which is represented by sigma of a semiconductor, depends on the number of charge carriers, and it is given by sigma is equal to Q multiplied by N mu E plus P mu H, where Q is the charge, mu E and mu H are the electrons and the holes mobilities respectively. They changes with the change in the dopant density, temperature and electric field. So the intrinsic electrical conductivity is given by sigma I equal to Q Ni multiplied by mu E plus mu H. So for the case of silicon, at room temperature, the intrinsic conductivity is equal to 4.3 multiplied by 10 to the power minus 5 ohm centimeter inverse. Now let us discuss the absorption of the sunlight. As the light enters and travels through the semiconductor, the intensity of the light, it drops exponentially. As the photons, they are converted to electron-hole pairs by the process of photogeneration. When a ray of sunlight strikes vertically on the flat surface of a semiconductor materials, a certain fraction of light will be reflected and remaining is transmitted through the semiconductor. The transmitted light can be absorbed within the semiconductor by using its energy to excite the electron from the conduction band to the valence band of the semiconductor. So consider when a photon is incident on the semiconductor, and if the energy of the photon is greater than the band gap, that is Eg, then it will be absorbed and it is converted into electron hole pairs or heat. So the intensity of the absorbed light or the intensity of the photon is equal to I naught exponential minus alpha x, where alpha is the function of the wavelength and it is known as the absorption coefficient, which is measured as centimeter inverse, and x is the distance into the material I naught is the light intensity just inside the surface of the semiconductor. Now the rate of the free carrier generation after the absorption of the sunlight is given by G, and it is equal to alpha NPH exponential minus alpha x. The absorption coefficient, that is alpha, it is related to the extinction coefficient by the expression, that is alpha is equal to 4 pi k by lambda. Absorption of sunlight. There are two major types of intrinsic absorption process which are used to determine alpha. These are direct and indirect absorption. The form of absorption process in a direct bandgap semiconductor is shown in the figure on the left hand side. Here, the photon momentum, that is k, equal to h by lambda, is small as compared to the crystal momentum. The latter essentially is conserved in the transition. In such semiconductors, the absorption starts at the photon energy of h nu greater than Eg, and the electron is moved vertically from valence to the conduction band without any change in the momentum. Now, as it is evident from the figure, which shows the plot of the absorption coefficient, that is alpha square, with photon energy h nu, there is a linear relationship between the two. The absorption coefficient alpha at near the minimum energy for absorption Eg is given by alpha is equal to C multiplied by square root of h nu minus Eg, where C is a constant, and for allowed transitions it is given as C is equal to 3.38 multiplied by 10 to the power 7 n to the power of minus 1 multiplied by square root of me by mo, this whole multiplied by Eg h nu, where Eg is the energy band gap, n is the refractive index, me and mo are the effective mass and the mass of the free electron. Now, the next is the indirect band gap semiconductors. In these type of materials, the minimum energy in the conduction band and the maximum energy in the valence band occur at a different values of crystal momentum. This is also evident from the figure on the right hand side. As indicated earlier, for the indirect transition of electrons from the valence band to the conduction band, photon energy h nu is required to be much higher than Eg. However, the transition of electrons from maximum energy valence band to the minimum energy conduction can take place at a lower energy by two processes involving the photon and the phonon. Phonon is a quantum particle corresponding to the coordinated vibrations which has high momentum but low energy as compared to photon. In this case, the minimum energy of the photon which is required to excite an electron from valence band to conduction band is h nu is equal to Eg minus Ep, where Eg is the energy band gap and Ep is the energy of the absorbed phonon of required momentum. Absorption of sunlight. The absorption is quite low for indirect absorption, that to pass a reasonable distance before it is absorbed. The absorption coefficient is given as alpha is equal to alpha A plus alpha E, where alpha A is due to phonon absorption and alpha E is due to phonon emission. The expression for the alpha A and alpha E are alpha A is equal to A multiplied by h nu minus Eg plus Ep the whole square divided by exponential of Ep by Kt minus 1, and alpha E is equal to A multiplied by h nu minus Eg minus Ep the whole square divided by 1 minus exponential of minus Ep by Kt, where A is a constant. Now in the case of forbidden indirect transition, the alpha is equal to A prime multiplied by h nu plus Ep minus Eg the whole cube, where A prime is a constant which is a function of energy and temperature. For indirect absorption, the plot between the photon energy, that is h nu, and alpha square is shown in the figure on right hand side, where we get two straight line segments. Now this has been indicated in the previous figure. The upper line intercept at h nu 2 on the photon energy axis corresponds to the emission of a phonon, whereas the lower line intercept h nu 1 corresponds to the absorption of a phonon. So the indirect band energy and the photon energy can be written as Eg is equal to half of h nu 1 plus h nu 2, and Ep is the half of the difference between the two. Now here in this segment, the absorption coefficient of various interesting semiconductor materials as a function of photon energy is presented in the figure on right hand side. The indirect band gap is small in the case of silicon and aluminium arsenide, where direct band gap is small in the case of semiconductor materials like cadmium telluride, cadmium sulfide, gallium arsenide, indium phosphide, etc. Solar cells made by using an indirect band gap material required a large material thickness to absorb significant light, and also since carriers are generated away from the collecting junction, so they required long minority diffusion lengths to reach the junction before recombination. So, in order to absorb most of the light, the typical thickness of the material varies from 20 to 50 micron for the indirect band gap material and 1 to 3 micron of a direct band gap material. Therefore, in a thin material, the homojunction should have very small area on the surface so that light can penetrate into the junction. Hence, the direct band gap material homojunction gives higher recombination, or basically the surface recombination losses. However, some of the problems are overcome by using a heterojunction structure of larger band gap material on the direct band gap absorbing material. Recombination process. The incident light of appropriate wavelength on the semiconductor creates electron-hole pairs. The concentration of these charge carriers in an illuminated material will be in excess compared to the dark. So if the light is switched off, these concentrations decay back to the equilibrium values. The process by which the decay in the concentrations occurs is called as the recombination process, which is also shown in the figure. Next, we will discuss about the radiative recombination. The radiative recombination is just the opposite of absorption. That is, under thermal equilibrium, an electron from occupied higher energy state makes a transition to empty lower energy state with the energy difference between the states same as the emitted light. This has been shown in the figure also. The next is the band to band radioactive recombination rate, that is U radiation. It is proportional to the product of the electron concentration in the conduction band and the holes in the valence band. That is, it can be written as the U radiation is equal to B multiplied by N multiplied by P. When the case of intrinsic semiconductors, where N is equal to P is equal to Ni, the recombination rate is balanced by the equal and opposite generation rate. So the total recombination rate can be written as U radiation is equal to B multiplied by Np minus Ni square. Recombination process. Now students, here we will be studying the Auger recombination process. In Auger recombination process, the energy produced by a recombination of electron with the hole is supplied to the second electron instead of emitting it as a light, which is clearly shown in the figure also. The second electron then relaxes back to its original energy state by releasing the phonons. Auger recombination is just an opposite process of impact ionization, where an electron-hole pair is generated rather than consumed. The band-to-band Auger recombination rate can be written as U Auger is equal to Cp0 multiplied by P minus Cn0 multiplied by N, this whole multiplied by Np minus Ni square. Also, Auger recombination process is more effective in highly doped materials. Now, the below table gives the values of the coefficients of Cp0 and Cn0 for the materials like silicon, gallium arsenide, and indium phosphide. Next type of recombination process which we are going to discuss is recombination through traps. As discussed earlier, impurities and defects can give rise to allowed energy levels within the forbidden gap of semiconductor. These defects results in a very efficient two-step recombination process as shown in the figure. Here the electrons from conduction band relaxes at defect level and then it relaxes to the valence band after annihilating a hole. The recombination rate via the defects of concentration, that is Nt, with a level at energy Et within the forbidden gap is described by Shockley-Reed-Hall formula, which is given as USHR is equal to Np minus Ni square, the whole divided by tau p multiplied by n plus n1 plus tau n multiplied by p plus p1, where n1 is equal to Ni exponential Et minus Ei by kt and p1 is equal to Pi exponential Et minus Ei by kt. And tau n and tau p, these are the minority carrier lifetimes whose values depends on the volume density of the trapping defects and the type traps. Next recombination process is surface recombination. Surfaces which represents severe defects in crystals and results in sight for many allowed states within the forbidden gap as shown in the figure. Hence, recombination can occur more efficiently at the surfaces as per above mentioned mechanism. The net recombination rate per unit area, that is UA, for a single level surface state is given by UA is equal to SESH, the whole multiplied by Np minus Ni square divided by Se multiplied by N plus N1 plus SH multiplied by P plus P1, where Se and Sh are the surface recombination velocities. Surface state level lying near the midway of forbidden energy gap are the most effective recombination centers. Minority carriers lifetime. It is possible to define the minority carrier lifetimes, that is tau E and tau H, under any recombination mechanism as follows, that is tau E is equal to N minus N naught by U and tau H is equal to P minus P naught by U. For radiative recombination, N minus N naught is equal to P minus P naught. Hence, the characteristic lifetime of a carrier can be written as tau is equal to N naught P naught divided by B Ni square multiplied by N naught plus P naught. The inverse of the lifetime is known as the rate constant, which is nothing but a sum of the different contributions to the lifetime. That is, 1 by tau is equal to 1 by tau radiation plus 1 by tau auger plus 1 by tau SHR. The effect of carrier lifetimes on transport properties can be by carrier diffusion, and they can be described in terms of the diffusion length as follows, that is, L is equal to root of D multiplied by tau, where D is the diffusion constant for the minority carriers in question. If, however, drift in the electric field E is the dominant transport mechanism, it is appropriate to define the drift length, which is as follows, that is Ln for electrons equal to E multiplied by tau n mu n, and Lp for holes equal to E multiplied by tau p mu p. This parameter plays an important role in the analysis of p-n junction solar cells. The available information for crystalline silicon has made it possible to arrive at an agreement that carrier lifetimes varies with temperature, doping concentration, dependence of the contributions to minority carrier lifetime. So students, let us summarize what we have learnt in this module. The incident light containing the photons of energy higher than the band gap of the material can be absorbed in the semiconductor by creating an electron-hole pair. Recombination of charge carriers in the excess of equilibrium values can occur through various processes. Radiative recombination is just the opposite of light absorption and an important mechanism for direct band gap materials. Auger recombination is important at higher doping concentration, whereas recombination through traps caused by impurities, and it is important for indirect band gap semiconductors. Recombination also occurs particularly effectively at semiconductor surfaces. Thank you.